In the framework of hypothesis testing, there are many decisions that need to be made by the researcher, and many of these decisions are going to have very many plausible choices that could be made that are going to be justifiable in certain settings. One of the key decisions that we need to make as researchers is what are the hypotheses that we're actually testing? And in particular, we need to decide, are we testing a one or a two-tailed hypothesis test? Now, there are very good reasons to pick one-tailed versus two-tailed hypothesis tests. However, we have to be very cautious with this decision because it's going to turn out that if you are a researcher and you're looking to do nefarious things with your statistics, you're looking to find statistically significant results at the cost of doing good science, it's going to be possible to use this decision in order to influence those results. And so there are good reasons why we should use one-tailed hypothesis tests, but we need to be careful about that. And with that care is going to come sort of a lot more critical thought around the context that we're actually working within. So the use of a one-sided alternative in hypothesis testing should only ever be motivated by the question of interest. If you are going to use a one-sided hypothesis test for your question of interest, you really should be making this decision prior to having collected any data. You should never look at the data that you've collected and then decide, okay, now I'm going to be running a hypothesis test that is one-tailed. Okay. And so we'll try to understand why this is the case. So what is the actual impact of doing a one-sided alternative in hypothesis testing? So if we use a one-sided alternative, only one tail is being considered in our distribution. Okay? And so this is either going to correspond to a single critical value or a single term in our expression for the p-value. The critical value is going to typically be smaller in magnitude compared to the equivalent significance level for a two-tailed test. And so if you're going to run a test with alpha equals 0.05, you're going to have a smaller magnitude critical value than you would if you ran a two-tailed test with alpha equals 0.05. What this is going to correspond to in practice is a larger rejection region in the given tail, right? And so it's going to correspond to a larger region that you can find statistically significant results in your specific tail. Now, the p-value is also going to be smaller compared to the two-tailed case in the relevant tail. And so again, if you observe something that is greater than the mean, right, and you have a alternative that suggests that it is greater than some threshold, right, then in that case, you're going to end up with a smaller p-value than if you had ran a two-tailed test. And so once again, this is going to correspond to finding a positive result at a lower level of significance than you otherwise would. And so ultimately, the impact of one-sided alternatives is that they are going to be less conservative than a two-sided alternative or a two-sided hypothesis test. So we can sort of consider what's actually going on. Why is that happening, right? And I think that it's probably easiest for us to think about this in terms of our critical value method. And so if we draw in here the sort of bell curve shape that we're used to seeing, and this could be a normal distribution, this could be a t-distribution, whatever the case, we take a look at our sort of bell curve here, okay? And then on this distribution, we can think about, well, what is going to happen if we want to run a two-tailed alternative, right? And so in this first case, we can think about testing theta is equal to theta naught versus the alternative theta is not equal to theta naught. And here we're going to find a critical value that's in the positive half at 1 minus alpha over 2, and we'll find a critical value at z alpha over 2. And the idea is that if we observe anything in the lower tail or anything in the upper tail, then we're going to be able to reject the null hypothesis, right? And so this red region here, this is our rejection region. All right, so that's our rejection region. Okay. Now, what does it look like if we run a one-tail hypothesis test? Okay, so we're going to start with a very similar looking bell curve here. Okay, and now we are going to be testing the null hypothesis, say that theta is less than or equal to theta naught versus the alternative that theta is greater than theta naught. Okay, so we're looking at this one tail alternative where the alternative is on the upper tail of the distribution. In this setting, we're only going to have a single critical value, and specifically, we're going to be looking at a critical value that comes in at z 1 minus alpha. And then what we say is, well, if you observe anything that is larger here, this is going to be your rejection region. And so, at first glance, there's no problem with this, right? Because at first glance, we can just say, well, sure, this yellow region here is larger than the corresponding positive red region. However, there's also that negative red region, right? And so if you observe something over here, well, that's going to get rejected. But if you observe the same thing down here, we're not going to reject that. And that's all well and good. That's sort of part of the justification for a one-tailed test. But now let's imagine that you had actually already observed your data point, right? And so you know that you've come in and you've observed a test statistic right about here, right? So that's your value here. And I'll plug in that value as Z. Okay. Now, in the case of observing Z here, notice that if you observed Z and you're doing a one-tail test, right? Then we are going to reject the null hypothesis. So we will reject it down here. But if you're doing the two-tailed test, you will fail to reject. And why does this matter? Well, this matters because if you've observed a Z and you know your Z is above the 0 point here, right? So your Z is above the critical or the test value, it's above theta naught, okay? Then what we're going to be doing is we're always going to be running this as our alternative here because you've already seen that it's bigger. And so then maybe you say, well, can't I just do a one-tailed test where I've already observed that it's bigger? And so if you are choosing what hypothesis you're going to run after you've seen Z, you're always going to end up in this situation. And then notice that because of that, you're going to end up rejecting the null hypothesis far more often than if you had used your two-tailed test. Because anytime that you observe anything that falls between this point here and this point here, right, anywhere in this blue shaded area, you're going to end up in a situation where you will reject it if you're using a one-tailed test, and you will fail to reject it if you're using the two-tailed test. And so if you've already collected the data and then you take a look at what you see and then you choose your hypothesis, the hypothesis test results are no longer going to be valid. Okay? And so it's important to recognize how using the one-tailed test in this sense is going to make a result that is less conservative, right? That we are actually going to result in more statistically significant results than we probably should. So what are we thinking about here? Well, we're really thinking about not wanting to do data-informed testing. Okay, so the process we just walked through, suppose that we calculate our sample mean and notice that it's below the null value, mu naught. Now, using this information, we could decide to test the null hypothesis that it's greater than or equal to versus the alternative that it's smaller. Remember, we already know that it's smaller, so we already know we're looking at that lower tail. And so if we decide to do this, then we're going to end up with too many false positives, right? We're going to end up rejecting the null too often. The test is no longer going to be valid at the given level of significance. Effectively, what we've done in this case is we've looked at half of the p-value that we should have actually gotten. We've cut that in half, or we've decreased the critical value because of this choice that we've been making here. Right? So if we had run the same test, would we have found x bar greater than mu, right? And so what we're saying here is just if you had gone back through the steps, right, and instead we calculate our sample mean and we notice that it is below the null. Okay, so we're in this situation. Is there any time that we're going to test an alternative of it being greater than, right? Or put differently, if we find that x bar is greater than, are we still going to be testing the same results here? And the answer is probably not, because if you find a sample mean that's bigger, then you're not going to make your alternative that it's smaller, because you know that that's not the case, right? What you observe is already contradicted. And so as a result, you can't look at your data to inform the hypothesis test that you're doing here. Okay, it's what we call p-hacking. P-hacking is going to be any process by which you artificially deflate the p-value based on the choices that you're making as a researcher here. Okay, so the decision to run a one-tailed test should have been made prior to seeing the data, and it should be informed by the context. You should really only care about one of the tails, and you decide to do that in advance. And then that way, it's possible you observe something below, it's possible you observe something above. If you observe something in the wrong tail, then you know you're not going to be rejecting the null hypothesis, but that's okay. Right? So it should be context dependent, but also made in advance. You shouldn't have already seen your data when you decide how you're going to test the hypothesis. Okay, so in this case, you might end up with a p-value that is half, but you might also end up with a p-value that's substantially larger. And that's why a one-tailed test is okay if you decide to do it beforehand. But if you look at the data and then decide what hypothesis am I going to run, that's where you wind up in trouble and into results that are not really trustworthy. So ultimately, all of this is to say that great care is going to be required in order to run a one-tail hypothesis test, and without this care, the results of a one-tail test are difficult to trust. The overarching advice would be that you should be running two-tailed tests unless you have a very strong, a very compelling reason to run a one-tailed test. The two-tailed test is going to be more conservative, it's going to detect differences in both directions, and sometimes that's going to be interesting, even if you didn't know that's going to be interesting. Now, if you decide to run a one-tailed test, this decision needs to be made before you've seen the data. As soon as you look at your data and then use that to inform what hypotheses you're going to be looking at, the results of your test are no longer going to be valid. They're no longer going to sit at the correct level of significance, and ultimately, you're going to be engaging in p-hacking behavior, which can lead to really erroneous scientific conclusions. So, you should take care if you're using a one-tailed hypothesis test and make sure that you're doing it for context-specific reasons.